Okay, thank you. Yeah, okay. So, yeah, so this is a some problem that the talk was discussing with us when he visited here last year. And it's a very, a simple problem. And we also had some idea about that. So we had a fun of discussing this problem. And I thought it is a good idea to share with you some of these ideas. So I think the full screen is not seen here. So join work with Anupam, talked and Ramesh. Yeah, so basically it is organized in this way. You have a small introduction and I'll state the main theorem. Then modulation space, a bit of review will be done. And then the main tool here is a Hermite function. So we'll discuss that briefly. And then we'll discuss the proof of the main theorem. And then there are some side results related to this. If there is time, I will discuss. If not, I will not discuss. So this is the way we will proceed. Okay, so let us recall that the classical modulation spaces introduced by Feitinger and later developed further by Feitinger and Giochini are a class of spaces which are invariant under time frequency translations. That you have you have a translation in the space variable and also modulation, which can actually be thought of as a translation in the frequency variable, because when you take Fourier transform, modulation essentially becomes the translates. So why are we talking about these modulation spaces in this context? So the thing is, among modulation spaces, if you just look at among this class, M11 will be the smallest and M infinity will be the largest. And these things actually among this thing you can easily check, but there is a general thing also. And so that will actually follow from the Feitinger's minimization principle. So that's a slightly general research. It's about Banach spaces, invariant Banach spaces. So what does this theorem result say? So if you have a Banach space, which is continuously embedded in tempered distributions, and further assume that is invariant under time frequency shifts, that is translation and modulations. And if it satisfies this kind of inequality, that is you have invariance with this kind of inequality. If you translate by x and modulate by psi, should have some omega x psi times norm. So invariance with this property, then you can actually show that this invariant Banach space contains the M11 omega with the weight omega if B intersect this at a non-zero point. So the moment it intersect, the intersection is non-trivial, then it will definitely contain M11. In that sense, there is this M11 is smaller. So similarly, you can show that there is a, we'll discuss this again. So this will be the maximum among all these things. So there is a thing is invariant spaces are actually sort of lies between this small one and large one under this condition.
A small clarification, Ratnakumar, can I ask?
Yeah, please.
Yeah, this tempered distributions has the freshest space topology, right? It's not a Banach space.
Yeah, that is okay. So we are only saying that I'm not, this is a Banach space embedded in this with respect to topology.
Yeah, it has a linear topology, not a Banach space topology, right?
Yeah, but B is a Banach space that's embedded in that.
Yeah, that I understand. Yeah, I thought maybe you are considering some other topology on tempered distributions. Okay.
No, it is the usual topology only we are dealing with.
Thank you.
Okay. Yeah, so I was talking about this because there's a this small space M11, and this large space L infinity is actually the dual, which actually plays the role of this. Let me. Okay, so I have a bit of difficulty. I'll get out of the presentation mode. Yeah. So so this space M11 here and M infinity. So if you look at these two, then this triple plays the role of the short space L2 and temporal distribution in general harmonic. So in fact, one can work with this triple in time frequency analysis. Okay, so I just said all these things, just bring in one thing. So Feitinger's minimization principle said that among invariant spaces, M11 is the smallest. Among invariant Banach spaces, M11 is the smallest. So what about Hilbert spaces? So, so what we are going to show here is such a, there's only one such, and that is precisely the L2. The moment you talk about invariant Banach, invariant Hilbert space, then this will be only L2. L2 is clearly an invariant space. So, so let us be more specific about these things. So here is the devastating theorem. Let me make it clear what we mean by the invariant Banach space. What we mean here is the sort of the so-called strong invariant space, which means that you want, if you apply the time frequency translations, then I have a bit of difficulty here. Maybe I'll go to presentation mode. Yeah. So the thing is, I want this norm to be preserved. This is what we are. This is the invariance you are talking. It is called strong invariance because you demand that model norm should be preserved when you translate by time frequency. Okay, so this is our definition of invariance. And here is the main result with that definition. So here is the theorem. Suppose H is a Hilbert space, which is translation and modulation invariant in that notion which I just now described, that norm of F should be same as norm of the time frequency translate. And H is continuously embedded in the space of distributions. And as usual, the intersection has at least one non-trivial element. Then such a Hilbert space should be L2. And you can actually show that with the norm is a constant times L2 norm of F. That's how we will be proving the theorem. Okay, so there's a small remark here. So here we are not saying that H is embedded in S prime, but we are making a weaker statement. H is contained in the space of distributions. But that actually what happens is because the translation invariance, we can actually show that this implies this, which we will be showing. I hope that nothing is missing here. Yeah. So let me state what that means. So here is the statement which I wrote as proposition 3. So suppose you have a Banach space continuously embedded in D prime with this translation invariant property. So what I mean here is I want the translate to be in the same Banach space with this extra condition. We already in our theorem we have actually equality. So this proposition you need only this condition. You just translate norm is less than or equal to, so this x 1 plus mod x to the r, this x translated x, times norm f b with some constant c, then you can actually show that this is continuously embedded in S prime. So from D prime, just translation invariance is enough. If it is embedded in D prime, then you can show that it is actually embedded in S prime. So this we will discuss toward the end of the talk if there is time. If not, I will not discuss. So here is, we have already discussed the minimization principle. So here, let me just take the maximization principle for the unweighted case, which again says that if you have a Banach space, which is translation and modulation invariant space, continuously embedded in the spacer distribution, and contains at least one non-zero element of M11. This is the condition we always put. Then B is actually contained in M infinity, provided you have this invariance condition. So if you translate and modulate, if you take this norm, should be constant as norm FB. So we will, there is time we will discuss a weighted version of this thing, but right now we don't need, therefore I'm just writing the unweighted case here. So basically it says that if you have translation and modulation invariant Banach spaces, they are, as long as they intersect with with the M11 at some non-trivial point, then you actually have, it contains M11 and it is contained in M infinity. Okay, so in particular, you have this space H, Hilbert space. We are putting this condition. So and you have invariance stronger than this, and therefore you have H actually contained in M infinity. And in fact, we have actually a slightly refined condition. So concentrate here. So H contains M11 and H is contained in M infinity, and these are continuous inclusions. So I think there is something below here. Yeah, so this is the point. So because H contains M11, which in turn contains short space, therefore it contains all Hermite function. In particular, it contains the Gaussian. This we will need, so therefore I'm observing it here. Okay, so
could you please recall what is Feschinger's minimization principle?
It basically told that if it is if the invariant Banach space has a non-trivial intersection, then it will contain M11. Let me see if I can show you the same slide. Yeah. Continuously embedded in S prime. And here, yeah, he has put this S prime. And you need only this kind of invariant, some moderate function coming here. Then if the intersection is non-trivial, then it actually contains M1. Yeah. So the point here was we do have at least the H node, that is the Gaussian, contained in our Hilbert space that we right now got with this observation. So now let us briefly recall the modulation spaces. Just to give you the definition. Okay, so as you know, this is defined in terms of short time Fourier transform. It is also called a windowed Fourier transform. The idea is you should have a transformation which actually gives some idea about the local behavior of the function. So we take a window, some short space function to be a window function, and then define a transformation which will have x and side dependence, because it is supposed to give us both this information. So here is the definition of short time Fourier transform. So basically, it is, if G is not that, it's just the usual Fourier transform. So what you do here is localize x around the localize the function f around the point x. For instance, if you take a smooth function to compact support, then this is just translating to that point. So it is just local Fourier transform basically. So the location changes, then you get the Fourier transform. So this is called windowed Fourier transform. You take a window and calculate the Fourier transform. So whenever this integral exists, we call it a short-time Fourier transform. So the thing is that this definition is for short space, where this integral clearly makes sense. You can also define it for general tempered distribution, because you observe that this can also be thought of as an inner product. So f with a bar or something, right? That bar you can think of modulation, translation of g by x, and then modulation by x. This should be psi or omega, I can't see properly. So it is nothing but m omega txg. So this is the this inner product. So L2 inner product. When f is in L2 short space, this can be thought of as in L2 inner product. Therefore, if you interpret this as a pairing for tempered distribution, so we do have this connection, right? So the usual pairing of tempered distribution into a short class function can be thought of as an integral if your tempered distribution is a nice function. So we do have this relation. The pairing is or if you look at f times the pairing h is same as the inner product f h bar if f and h are nice functions. So I only want to point out that you can think of this in inner product, and that allows a generalization of windowed Fourier transform to tempered distribution in view of this pairing. Pairing is this one only. Looking at the case of nice functions. So yeah, so you have basically a sesquilinear form because the bar we took in that pairing. So, and this is actually a nice function. You can get easily short say from the continuous function. Okay, so then modulation space is, as I told you, it is defined in terms of this windowed Fourier transform. So you have to measure this time frequency concentration in some way. So in modulation space, what they do is to take this mixed LP norm with us to some weight W and define a norm like this. So you take VG of xi and then first integrate, take a weight and first integrate with respect to x, taking care of that LP norm with respect to x with this weight. Then you take LP norm with respect to psi. So that gives a norm, and all this distribution for which this norm is finite will be called in the space MPQ with weight W. So when one of this is infinite, you need to define it as a norm. Yeah, there are weights of this form, which is moderated. You will see such things here, which when you translate some moderate function will come times this kind of thing. So typical examples are power type weight of this form, and that has a special importance in this analysis. Okay, so when weight is 1, you just denote it as MPQ. That is what we are discussing mostly, but such as you call this as below. And another thing is this definition does not depend on the window function because this relation you can see in your book. So it doesn't matter which G window function you take, you end up with the same space. Okay, so that was a little bit about modulation space, because I was talking about here and there modulation, so that's why I just talked about this. So now let us recall this Hermite function, because this is the main tool that we'll be using here. So what are Hermite functions? This all of you know. So let's look at the one-dimensional case. So you just take this Gaussian, differentiate n times, so you get a polynomial times e to the minus y square, and you multiply with this, so that is polynomial times e to the minus mod y square by 2. So your short class function. So you normalize so that its norm is L2 norm is 1. So this is for one dimension. For n dimension, you can simply take the tensor product of the one dimensional and get the n dimensional Hermite functions. So they are eigenfunction of the Hermite operator with the, of course, eigenvalue 2 mod alpha plus d. D is the dimension. Alpha is, if H alpha is the Hermite function, then this eigenfunction with the eigenvalue 2 mod alpha plus d. So here, this is what we are now going to use. This Hermite operator can be represented in terms of annihilation and creation operators. So what is the annihilation operator? Here is the annihilation operator, ddx plus xj times 1 over root 2. You take some normalizing constant. Then creation is minus ddxj plus xj. So why are they called annihilation and creation operators? Yeah. So let me see, something is missing here. Yeah. Let me see what. Yeah. So they are called annihilation operator because let's look at creation operator. What does it do? Creation operator, you take H alpha to the next level with this constant, depending on alpha, and annihilator operator bring it down to the previous stage, alpha minus Ej, where Ej stands for the vector or index with the 1 at only non-zero term, 1 at the jth place. So I think it's easy to see this for one-dimensional space, one-dimensional Hermite functions. So more generally, for any dimension, you can have this annihilation and creation operator. The advantage with this is that you can go from one Hermite function to other using these two operators by successive application of this annihilation and creation operator. So let us look at define A alpha for any multi-index alpha. You can define A alpha by just take the product Aj alpha j. Similarly, C alpha you can define in this way. So that by successive application of this, you can see that if you take H alpha and apply alpha times, alpha is a multi-index. So then you end up with H0 with this alpha factorial to the R. This is a multi-index, so that means if alpha next to alpha n, it will alpha 1 factorial to the R, etc. alpha n to the R. Similarly, for creation operator, if you take from H0, you can reach to H alpha by applying C alpha. Of course, this constant also will proper because of this thing. Okay, so the main thing or main idea by which our proof will work is this these relations. Okay, so what does this say? So I mean this relation, this kind of Hilbert space. So I have an invariant Hilbert space. I mean translation and modulation invariant Hilbert space. Remember here invariance is strong invariant. That means you apply the time frequency translation, your norm should be the same. That's crucial in this argument. Okay, so for such a space, what is the statement? It says that you take any of G in H, this abstract Hilbert space, and Xi in RD. Yeah, so this is not really abstract, and that it is a spacer tempered distribution on RD. That's the kind of thing we are looking at here, because we are talking about invariance, translation, modulation, etc. So only up to that much it is abstract. Okay, so what is the thing here? So so for any FGH and X psi in RD, what we have is, look at the inner product of translate of F with G, that is same as F with the translated G by minus X. Same modulation of F by this psi, inner product with G, same as F inner product G tied to the plus IX dot psi H. Okay, so and the next one is, so from this actually you can show that this inner product d alpha f g is same as f minus d alpha g inner product with h. Similarly, x to the alpha f g same as inner product of f x alpha g. Okay, I think I didn't do something carefully here. Here by this inner product, I should use this kind of notation because I'll make a distinction later. Okay, so okay, all these are very trivial for L2 because you just use the translation invariance of the Lebesgue measure. This will follow. Similarly, this will follow by integration by parts. But we are not working with any in L2, but it could be some kind of abstract Hilbert space. So, but there it is still valid there. In fact, it is actually a simple idea. In fact, it just follows trivially sort of from the this polarization identity, because what we are demanding is translation and modulation invariance. So the norms are preserved. So therefore the inner product, because this relation, you will have the condition automatically follow because of this polarization identity. So once you have these relations, you can just differentiate and obtain the other two conditions and evaluate at x equal to psi equals 0. If you look at the statement, if you look at the statement, there is no x, nothing is, no psi or anything is just input. And also notice that when we talk about derivatives, here we are only talking about Schwarz class functions. So therefore, all this differentiation, multiplication, etc. makes sense. In this statement, this is only for Schwarz space, whereas this is valid for any G in H. Okay, so the thing is, once you have that kind of invariance property, that is, what are they? So this translation invariant, I mean, this translator, then it goes to translation by minus x, just like in L2. So this modulation is, and that basically leads to this kind of condition. So because of these two conditions, we can actually get this relation, because this Cj and Aj, if you look at, they are differentiation and multiplication, right? Multiplied by xj. So those conditions basically tells you that you have this fcj equal to aj fg. Again, for L2, we know this is trivially follows, because by integration by parts, etc., can show that cj is nothing but the adjoint of aj. So what we showed here, the same thing is true in this invariant banner, invariant Hilbert space also. Okay, so this is important for us. F inner product of Cj is same as AGF and G. Okay. Okay, so to prove the theorem, we need a little bit of preparations. So this is some observation that is crucial here. So we have already, I think we have maybe edited. So we all know that the pairing on S cross S prime, that is the short space paired with the tempered distribution. If the functions, the tempered distribution is also a nice function, say short class function itself, then this pairing is nothing but integration of this f with the integration of let's say f with the g, f from here, integrating f from against integral g. That is how you get the pairing. So this is nothing but the L2 scalar product. So in other words, the pairing here, how do I put this? Yeah, I have written here. So you look at this. For lambda, a tempered distribution, phi Schwarz class function. So this is the expression if lambda is a nice function. For instance, lambda is a Schwarz class function. So this pairing, you can think in terms of L2 inner product. So basically, this L2 scalar product, which is actually a sesquilinear form, that gives the a pairing on the distribution. Okay, so that is a crucial thing that we use. So the pairing here can be identified through the L2 inner product. So using this relation. So this lambda phi, same as inner product lambda phi bar. So this is why I said I'll be using distinct notation here. For H also I'll use this kind of thing. For distribution I use this sort of notation. Okay, so yeah, this I cannot move. There's some problem here. Yeah, this I already told. And yeah, so the other main point is, as we just now verified some properties of Hermite function on the on our abstract Hilbert space, we can actually show that Hermite expansion is valid on this Hilbert space also. So the point is, the claim that we are making is, look at this Hermite function, normalize with H naught, norm of H naught inverse, then it is an orthonormal system for H. Okay, so this again a simple idea using these relations. So the creation operator, you can H naught, H alpha can go with annihilation operator can come down from H alpha to H naught. So just by using this, you can show that they form an orthonormal system. So let us do this. Again, this is the usual inner product notation. Okay, so this inner product, using this relation, I can write H beta as C beta of H naught, because the creation you can reach here. And we have already seen this adjoint relation is valid. C I can bring here as A, so that shows A beta H alpha H naught. So that is the point. So the point is, H alpha H beta can be written in this way. A beta H alpha H naught. So what is the consequence of this relation? Suppose alpha and beta are different. So at least one of them, say I choose in such a way that beta j is larger than alpha j. If beta j is larger than alpha j, then I use this calculation. If alpha j is larger than beta j, I will interchange this. Okay, so If alpha and beta are two indices which are different, then you will have beta j larger than alpha j for some j. And then what will happen to this quantity? If beta is larger than alpha j, this is an annihilation operator. You apply too many times, it will kill it. So that means the conclusion is alpha and beta are different, then the inner product is 0. And what happens when alpha equal to beta? So we have the same relation again. Yeah, here, look at this. A alpha H alpha is H naught itself. So the same relation will give beta equal to alpha. You get the inner product H alpha H beta is something times inner product H naught itself. So you have this cancellation here. So you basically get this condition. So this actually gives L2 norm of H alpha square is equal to L2 norm of H naught square, because this nothing but this together is nothing but H naught square. So here you have this relation. So that shows that they are an orthonormal system, because they are orthogonal and the norms are no, they are orthogonal. So if you divide
Yeah, I think there is some connection issue.
Speaker is not speaking.
Yeah. Yeah. Maybe there is a connection issue. Yeah. Okay. I think he'll rejoin. Yeah, he told me his connection is a little shaky, so let's wait.
Otherwise, Ramesh has to continue.
Yeah. Or Ramesh can, yes.
I think Anupam could continue because she is the co-author.
Anupam,
Oh.
Ramesh, yeah. Okay, I think he's back.
no, can you hear now?
Yes, it's
So
echoing.
I may have to log out and log in.
I see. You can share your. So now it's okay? Hello? Yeah.
I'm trying to.
Okay.
Can you see now? I think there is some problem.
Yeah, we can see. Yes. I think you have to unmute yourself.
Yeah. So we will work with this. Yeah, we will work with this normalized function so that yeah, the claim is I'm taking only Schwarz class functions here. Then the claim is L2 norm of the Schwarz class, norm of the Schwarz class function with this norm is same as L2 norm of it. So this you can get by writing this Hermite expansion, which is valid for F in Schwarz space. Okay, so there's a bit of problem here, I think. So we can argue it in this way. You can actually write this because there's connection between inner product and the pairing that we just now discussed. This connection here. What you can do is write this L2 norm as this pairing. This is inner part FF that can be thought of as pairing. Then you can write this part as okay. So now I'll go to presentation mode. So now this part, first one I can write is in the tempered distribution sense, and then this is a Schwarz class function. This action makes sense, and also I can interchange this sum because the convergence is in the tempered distribution, the space of tempered distributions. Therefore, this is valid, and H alpha F bar is nothing but okay. So okay, so this is not seen here, so I can tell them. So notice that this inner product F H alpha and H alpha F bar is nothing but this inner product of H alpha with F in L2 you can think of. Yeah, we are here. I don't know what is happening here. Yeah, so I think something is missing here. So let me try to explain here. Yeah, so as I pointed out here, this pairing you can think of H alpha, inner product H alpha F, so that is the bar of this, so therefore it is valid. So you use this tempered distribution argument, then this is clear. Okay, so we are here. So I said we'll work with the original norm, and so that is an orthonormal system for H. So we have this identity for Schwarz class functions now. That is what we are. Okay, so here there is an argument. Yeah, so this is what I was looking for. Because of this condition, we have that equality. And so what we have proved is that identity only for Schwarz class functions. But now we have this into L2, this is a dense inclusion. Therefore, it follows that you actually have L2 is continuously embedded in H, because that relation that you proved, that identity that you proved is only for Schwarz class, but for using density, you can actually show that L2 is, it actually follows that L2 is embedded in H in a continuous manner. So So now what we showed is, we want to show that L2 is equal to H. We have shown that L2 is contained in H with the continuous inclusion. And so we can show that this is actually equal to L2 by using Van-Banach theorem. So here again, a little bit of playing around Hermite function only. So again, so suppose L is a linear functional which vanishes on this subspace. N is a linear function on H which vanishes on this subspace. So any such linear functional we know will be given by, this is inner product, inner product in H, inner product of F with the G naught for some G naught H. We show that G naught equal to 0, that will prove that L is identically equal to 0. Okay, so why is G naught equal to 0? Remember, this G naught was in H. So that is actually contained in temporal distribution. So you can show that G naught equal to 0 by showing that all its Hermite coefficients are 0. So yeah, because the temporal distribution actually have a Hermite expansion, the polynomial can have at most polynomial. That much we know. So we can straight away write down the Hermite expansion and use the given condition to show that all these coefficients are 0. Okay, let me try to do this. Yeah, so when you try to write down the Hermite expansion, here is the Hermite expansion. Hermite expansion here with C alpha, you can either write the usual, because we have an identification here, that is what we will use here. So as a temporal distribution, it is G naught acting on H alpha. Remember, this is a real function, so there is no issue here. G naught H alpha, and this C alpha, the coefficient is nothing but this, it has at most polynomial group. Yeah. Yeah. So what? So these coefficients are given by the pairing of the temporal distribution, and the pairing of temporal distribution is related by the L2 inner product. So I mean this with that identification. So what you have is this G naught H alpha. The coefficients are nothing but G naught H alpha. So yeah, this is that connection I just said that. Okay. So so now we need to show that the coefficients are 0 using the given condition. So what is, so we have C alpha equal to G alpha, G naught H alpha, and this is nothing but G naught H alpha, this usual L2 inner product. And this we saw, this inner product, these are the same pairing it is, I mean same inner product. And this I can write as the conjugate of H alpha, G naught H. Yeah, so what is this quantity? So C alpha can be finally expressed in terms of this Hilbert space inner product. So what is this quantity? This is nothing but the linear functional acting on H alpha. G naught, H alpha, G naught bar, H alpha G naught was L G naught. This is L G naught bar. So this quantity is actually going to be 0 for all alpha. So what we conclude is C alpha for the Hermite expansion, all the coefficients are 0. That will show that G naught is actually equal to 0. That means the functional is actually 0. So if you invoke Van-Banach theorem, this shows that this subspace has to be dense subspace of H. But now L2 is also closed subset of H, because we have already proved an identity here, so that there was an inclusion we had proved, right? identity for Schwartz class. We have proved an identity, and that extend to L2, but the inversion from L2 to H is actually continuous. So this is actually closed tendence. Therefore, that will prove that H equal to L2. So yeah, there are some properties, etc., which I was supposed to talk. Maybe 5 minutes I'll take and just tell something about it a little bit without talking much about it. So my time is over, right? I don't know when it was started.
Yeah, it was delayed a bit, and then in the middle also there was some disruption. So you can take 10 more minutes.
Should I take a bit more? Up
Yeah.
to you.
Yeah, please, you can take more time.
But should I? Okay, maybe I'll discuss this thing. It's an interesting, this interesting proposition. So this was the proposition which we already mentioned before, that if you have a Banach space that is continuously embedded in D prime, then it is actually embedded in S prime. So from embedding into larger space, you can show that it is actually embedded into a smaller space. So this will be valid if you have just the translation invariant. Even this much kind of condition is allowed. You don't need strong invariance. Even if this translation by X is bounded by 1 plus mod X to the R times this original norm, that's also enough. Then you can show that is continuously embedded in S prime. So there is a small refinement because of this thing, because fighting is minimization property, which was originally for things embedded in S prime. Because of this result, you can actually show that it is actually valid for any Banach space continuously embedded in D prime actually. So that is a consequence of this result. Okay, so the proof that comment was just about the proof. Yeah, so here I think I can skip this. We know how to identify short space as a space of tempered distribution, right? So this I will talk about. Yeah. Okay, so then let us try to prove this theorem. So what exactly we need to prove? Let us look at the statement. Okay, so you have to show that B is continuously embedded in. This has a locally convex topology. So this was a Banach space. So you have to show that this Banach space is continuously embedded in this locally convex space. So remember, these spaces. So they are defined by these are actually what is called the Weak-Star topology, and they are how do you say, the corresponding semi-norms are given by Schwartz class functions. Okay, so the point is because of this. First, let me say what exactly we need to prove. Then I'll prove that. Okay. So because if it was if it was into a Banach space, what we will be doing here, we'll show that norm here, the range IF. This is the inclusion map. So this IF, its norm plus the norm of F, the Banach space norm. That's what we do. So because this is not Banach space, but just a locally convex space. So then what you do is you just prove boundedness of this map, and boundedness is then used in terms of the semi-norms. So because this Weak-Star topology, the semi-norms are given by again the Schwartz class functions here. So maybe P psi or something like that you can write. This is something like P psi F is equal to norm F times norm psi. So we basically want to establish such an inequality to show that the inclusion is continuous. So let me highlight. We are trying to just show this thing. Inner product, this action F psi less than to norm Fp times psi. Where this constant should be independent of F and psi. So once we establish this inequality, then we are through. So let us try to do this. So remember, psi is an arbitrary short-class function. F is in the Banach space, which is ultimately contained in D prime. So yeah, and another thing is, yeah, the another important thing here is, again, ideally I am supposed to do this for short-class functions here, but it is enough for me to take functions from D of Rd. Then CC infinity of Rd, because the density, because it's enough to establish this on a dense class. So we will only prove this for sin C0 infinity. We have to ensure that the constant is independent of F and psi. Okay, so yeah, and this is actually yeah, let me come back to the proof. Okay, so I want to show that inner product F psi less than norm F times norm psi for taking psi in the Shas class. So the basic idea is using a partitional unity to ensure that you have this uniformity. So we use this notation. Japanese bracket for this term 1 plus mod x. And so you take a cube for some epsilon quantities, you look at the cube 0, 1 plus epsilon to the d, slightly larger cube than 0, 1 to the d, and take a phi supported in CC infinity, support in this. Yeah, phi is supported in this, and this is a partitional unity. So you can, by taking slightly bigger, and you can sum over G and get a partitional unity like this, because support is slightly larger is possible. Okay, so what is given to us is this: the embedding B to D prime is continuous. So that translates again by the same thing as I told you, that because the big star topology is here. So this condition is exactly this thing here, because the norm here, and this is the kind of semi-norm acting on psi node. Yeah. So what do we want to do? We want to bring in, what is it? What exactly wanted to? What is the psi node?
I think it is for any arbitrary CC infinity function in Q, right?
I think he lost connection again.
Yeah, again, I think, because I cannot see. Okay. Yeah.
with the same norm, and then so that that Hilbert space is exactly equal to the L2, means L2 of
Exactly
R2.
equal to.
Yes.
You can't deduce this from Stone-Farnheimer theorem. If you have a Hilbert space which is invariant under these things, then you can define a representation, right, on the of the Heisenberg group on that. Then this Hilbert space will break up into several pieces. Each one will be, on each one you have a irreducible representation, and then that has to be unitarily equivalent to L2. So how does it become just a single component?
I think there is this embedding also, no?
There is something missing. I mean, I don't know. Is there some extra assumption on this Hilbert space?
Yeah, I think.
Yeah, Hilbert space has these two, means it's translation and modulation invariant, also which contain at least one element in that M11 minus 0, and it's continuously embedded in the D prime of RD, means the distribution.
Oh, so many things. So you can't start with the Stone-Farnheimer theorem and then deduce it quickly. Is it possible?
I don't think that it is possible from that.
No, you have a Hilbert space and you have a invariance. So immediately you can say that that is a direct sum of several Hilbert spaces. Each one is unitarily equivalent to L2. So then you put these extra assumptions and then just show that only one survives.
Yeah, here you are taking separable Hilbert space, right?
Yes.
Yeah, separable only.
Yeah.
You can't do that. No, you didn't try.
No, I did not.
No, but it is unitarily equivalent, but then that embedding will show that it is like actually L2. No, they are saying that it is equal to L2.
Yeah, they are saying that it is equal to. So once you prove that the Hilbert space is, I mean, you have to show that the representation becomes irreducible. Then the Hilbert space is equivalent to L2, and then some assumptions like a distribution or something that will force that to be the L2 space. I mean, possibly, I don't know.
Possibly, I think, yeah, maybe the
There should be
different proof. Yes.
Should be some easier, I mean, quicker proof using that.
I think this proof is also simple
Also
in the sense
simple.
that they just use the sesquilinear form. I think that was the and
Yes.
also right, that uses the translation and modulation thing, no, to say that the inner product with the Schwarz class is the L2 inner product. No?
L2 inner product, yes.
Yeah. So there you use this fact that it is invariant under right, translation.
Yes, translation and modulation.
Yeah, maybe using Stone-Farnheimer theorem also one can have a proof.
Give a different proof, yes.
Yeah, I think yeah, we'll have to end the
I don't have
meeting.
any other question.
Yeah. Any other questions? Yeah, so yeah, Ratnakumar has sent me an email that he will not be able to join because the network is very slow. So, yeah.
Okay, thanks the speaker.